Okay, well, welcome everyone. By the way, the reason I'm dressed is not for this celebration.
No?
I just
Disappointed.
had an hour-long interview that ended up half an hour ago with Ian Bremer from has a program called Ground Zero on PBS. And I should tell you that one of the key questions that he asked was about black holes, and he was very excited about this image that we will soon celebrate. And I didn't lose that opportunity to tell him the story about the sewer at my home that got clogged by tree roots, and that led me to think about what happens to matter when it falls into the singularity. Just to put things at an elementary level. And illustrate how much we don't know about what's going on inside black holes. But the reason we know more than we knew years ago is this beautiful image, and by the way, you can't see it and I don't want to tilt it, but the image appears as part of the cake that we will cut very soon. And the idea is, you can cut the shadow, nothing bad will happen to the knife, and we will all celebrate this wonderful image that got the attention of everyone, I should say, and appeared above the fall of a lot of newspapers. But we will start the celebration with a wonderful clip that Peter Garrison produced as part of a film that he is finishing, right? Peter, when is the film going to come out?
It should be finished in early fall, September.
See, when a woman is about to give birth, we can tell. When you are about to give birth, we can't tell. But within 2 months or so, 3 months.
I should be able to show it here.
September. Okay, and we see the first clip from that film that illustrates the excitement of the discovery. And then what I would like to do is go around a group of people that were involved in making this beautiful image, all the members of the EHT collaboration, some of whom we saw featured on the media recently. And each of them will tell us for 5 minutes the highlight of their experience with the Event Horizon Telescope. So I would like to invite the members of the EHT in a few minutes. It will take 9 minutes for us to watch and so within 9 minutes, be ready to step up.
Seeing is believing. That's the most credible and the most powerful sense that we have. We need to see things. We long to see things. In my mind, like for 10 years, there's no question there is a black hole, and there's no question it's possible. I still want to see that stupid image. I want to see it.
The Event Horizon Telescope is a new instrument that a global team is assembling that will have the magnifying power sufficient to resolve the region immediately around a black hole. We want to image an event horizon, take the first picture of a black hole. It's very difficult to do that. A black hole is very elusive. It's very small.
To see the black hole, we need an Earth-sized telescope. We can't do that, but the next best thing we can do is set up telescopes around the Earth that can talk to each other, that can record data in tandem, and time tag it so well exactly when each waveform arrived at each telescope. We can combine these data and make the telescopes act like they were actually one telescope. So the Event Horizon Telescope is right now an array of 9 dishes across the globe, from the South Pole to the Arizona desert to Hawaii to Chile, creating effectively an Earth-sized telescope.
In 2008, we joined this project. It's like maybe 25 people. It's relatively small. And now we are more than 200 people spread all over the world. Very international. So it's getting bigger and bigger, and getting more complex. But what is really exciting is we have more stations. That is really fundamental to getting good images.
So over the past 9 years, what we've done is slowly build the array out. We've gone to new sites, and we've had to convince those new sites that the science is worthy, and we've had to install very specialized and expensive equipment at all of these sites.
We are pushing state of the art, always. The photons we detect and the signals we pick is so faint that it wouldn't work with anything that's available normally. So we're inventing new technologies that's on the cutting edge. We're building superconducting receivers, we're building digital signal processors with more and more processing power. I find it so exciting to be at the cutting edge.
And April 2017, all of that was ready. We had a time period of about 2 weeks where all the telescopes were willing to give a number of days to be part of the Event Horizon Telescope Array. SMT technically ready, weather forecast possible of high wind, but unlikely to cause anything. So SMT go, we needed good weather. We needed good weather simultaneously in 6 places all over the world. AX, technically go, weather excellent. I think should go on that column. And we were very likely to actually have that good weather happen practically day after day after day, to the point that we were all exhausted.
We have been so fortunate with weather. Every single telescope that we wanted to be on is on.
Final scan, so you guys can start with us.
This is it. Oh yeah, this is it. So this is it. The final scan of the 2017 observations. And then you really begin to feel the excitement. You really feel that you're going to see something that is new and that nobody else has seen before.
Shut, close the doors.
You ready? Wait, what is happening?
We're trying to make an imagery now.
Can we just like case things a little bit?
Well, no, first of all.
When we take a picture on our camera, right? You believe that picture is exactly reality, right? You actually saw that with your own eyes, and you can see, oh, okay, that matches. When we take a picture of a black hole with the Event Horizon Telescope, we don't get to see that. We don't know if the picture we generate is actually what the black hole looks like. And so we have to really think about this problem in a lot of different ways so that we're really confident when we get that picture.
The end goal is to have this snapshot of reality, how a black hole really looks. You could imagine if you're holding a flashlight behind a black hole, that some of the photons would be far enough away they'd just come to you. Some of them would be close to the horizon, and they get bent inward, but they would still make it to you. And some of them would be too close, and they'd fall into the black hole. And so the shadow of the black hole is this region where the photons behind it are getting trapped. And so it's a circular area of diminished brightness, and this bright ring around it. I think it's rare in research to have such a concrete prediction for something that no one's ever seen.
Just go check my audio.
Can you hear me?
Yeah, I can hear you.
Hi Monica, can you hear us? Okay, so I just want to start the first one, which actually showing the first images of M87. I think the images are broadly consistent. There is a shadow-like feature.
Wow, it worked. I mean, it definitely worked.
It was surprisingly emotional. You know it from a mathematical point of view, and we've been looking at pictures quite similar to that from our own models. But when you look at it, and you have to tell yourself that it's actually data, that you're not seeing a simulation, but you're really looking at a black hole. I found myself just with my cell phone staring at it for hours.
So we see this ring. It's phenomenal. It's the result of my lifetime. We've seen the shadow of a black hole. But this story is just beginning. We've opened a window onto the event horizon that we never had before. We don't know how this book is going to end. All we know is that the first chapter has us hooked. And that's enough.
Images for the film. She's a great animator here at Harvard. I mean, it's a fantastic team. Child King, many of you have met, is the editor. He edited Fog of War. I've been working with him for 15 years on secrecy and containment and other films. So it's a terrific team, and I hope many of you will be joining us this evening for a party at my house. I've never given a party of this scale before, but I've never been in something so fun as this in my entire life. So I thought, why hold back now? If not now, when, as the saying goes. So.
And we are so privileged to have you with us and benefit from your expertise and from your filmmaking abilities. Thank you.
Thank you.
As many of you noticed, the walls, the scenery in the movie took place. Yeah, it's familiar. It's here, the Black Hole Initiative, and we are really proud that this place gave birth to this culture of black hole enthusiasts. That among them the Event Horizon Telescope team. So I would like to invite the members of the Event Horizon Telescope team to the forefront, and each of them to say in a few words, just a couple of minutes, what the experience was for them. Please come over. Yeah, everybody.
Nobody left.
Everyone that is more than 6 meters.
We're all, I mean,
yeah.
I think half the audience.
That's okay.
Don't let Michael avoid. Michael, I saw you out there.
Where's Michael?
Michael.
Michael's.
Michael.
He's behind you for us.
Oh, he's right here.
You'll disappear. You'll be spaghetti eyes.
I don't think the order matters because, as you will see, it's we'll get a coherent picture. So let's start just based on the order that you stood up, and then yeah.
Michael, if he's any.
That's okay. But I should speak about your personal experience rather. You don't need to describe the project as a whole. What was it for you?
Oh, for me, it was an absolute blast. Kind of two parts of me were involved. One part, I was back as a graduate student. In this room, I was making images. In the joint PI office out there, we were doing, other telecoms and strategies. Right here, I was just doing science, learning actually from all the young guys, and contributing to those papers, including actually one that we didn't do here. simulation. I was running simulations like everybody else, and I was actually making simulation data. That's one half of me. The other half, I had a role also as, the big senior person, because I had to kind of organize the way the publications went. I had to do some refereeing.
But also maximum entropy for the images.
Oh yeah, that is my student life. But the half that the seniority came in was also, as it happened, useful, important to get the project on track when things were getting a little sticky. So yeah, so for me it was really wonderful to be on both sides of, at the top level, in some sense, and
in the trenches.
And in the trenches, very much in the trenches. Yeah.
Okay, so I'm Jonathan Weintraub, and I work for the SMA, and I do digital signal processing and engineering instrumentation for EHT. And I think I recognized this when I was preparing to give the talk at the Science Center. That really I got hooked on the EHT in basically 2007 and 2000. I think it was 2007. And Shep had kind of recruited me to go do some early experiments. And we did this 3 baseline experiment from Hawaii using the JCMT reflector to SMT in Arizona and a single comma dish in California. And I remember some months after the observation, which was in March and April, I was walking my dog with my wife, and I think we were wheeling a stroller in the Arboretum, and Shep called me to say that we got a detection on Sergei Star. Which nobody knew you could do on a long baseline. There had been the Krichbaum result between France and Spain, rather marginal. That detection was, there was a short baseline from Arizona to California, and there was a whole cluster of about 20 detections on that baseline. But then on the long baseline from Hawaii to Arizona, there were just 4 detections. And every other scan represented on the short baseline was a non-detection. And there were no detections whatsoever from Hawaii to California. But we knew California was working because we had detections from California to Arizona. It was really a threshold moment because, I say the risk is retired. A lot of people say I shouldn't say that because it sounds like a business term, but I think we knew it would work. And we just had to throw more engineering at it. And more instrumentation, more bandwidth, more. Indeed. Yeah. There was no obstruction.
But by the way, I should mention that Jim Moran sent out an email yesterday showing a document from 1984 that was written at the Center for Astrophysics, in which they tried to advocate for the SMA. Erwin Shapiro was the director, and they said one of the things you can do with it is get an image, perhaps, or constrain the shadow of a black hole, of a supermassive black hole of the type of energy. So this is in writing from 1984 at the CFA.
It was probably Colin Masson's memo.
No, it's not a memo. It's actually a document, like a report.
Right.
And actually Mark Reed is on it. Several other people. Anyway, Shep.
I'm gonna pass over me. Go right to
Why?
No, come back to
I want to hear Shep's story. What the hell did you do?
I'll speak at the end. How about that? Go ahead.
He's reserving the end spot.
It's okay. Just say what it was personally to see it come to fruition in the way that it did. It's just the end point.
So I've been working on this for a long time, really since I was a grad student in the 90s, thinking about high frequency VLBI, trying to get the greatest angular resolution possible from the surface of the Earth, and we did this by going higher in frequency with this technique called very long baseline interferometry, which turns the Earth into a telescope. And it became apparent that this kind of thing was possible, and then we had to go do it, because you can dream something, but then actually making it come to fruition is joyful, but also incredibly stressful. I can't, and it's very important for us to recognize the
human side, you mean, or the technical side?
The human side.
The human side.
The human side.
That's what I thought.
I do want to stress that there are significant others associated with many of the people here, and my hat's off to them. You have a group of people that is so obsessed. You also have a list of significant others who are driven crazy by this whole enterprise. And then, as Jonathan said, we had this watershed moment where we could see these small structures. And then we've been building out the array, and I'll just end by saying that probably the thing that's most gratifying is the team that we built. We had an amazing team of people, and many of them are right here, and I am just in awe of all the people that have been working with us on this, from graduate students, even undergraduates have played key roles, graduate students, postdocs, Michael, Michael Magic Johnson. Michael was an extraordinary, addition to the group, and he came to glue the lid off things, and then around the entire world. And you need a global team to build a global telescope, and that's been the thing that's most gratifying.
Chef, the most unusual thing I heard from you was
Wait,
even though
there are a lot of unusual things.
but even though the technology was not demonstrated before the project, and it's extremely challenging technically to accomplish, and that's what you worked on for so many years. It's the human aspect that is the most challenging. That's really interesting because, I worked on another project where people said the policy aspect of it is much more challenging than the physics aspect, and often humans are more challenging than the physics, the underlying physics.
Well, you need a group like this who's willing to
work together. Yeah.
Who's willing to commit, because the times are challenging.
Interesting.
Yeah, it's been extraordinary. I mean, there's this interesting dichotomy that I've been trying to place, which is that working here, you're working with all these people who are incredibly brilliant, often in topics that you've never studied before. So you're just constantly being pushed to your absolute limit, both in things that you're supposed to be an expert on and things that you're doing for the first time. So we're being stretched as far as we can possibly go, and I think we're just pushing each of all of us to the brink. But at the same time, with such a big collaboration, getting a result on your own means almost nothing. And so, we gathered here to make the first images that we saw in the film. We made them, and it was sort of this transcendent experience. I mean, we'd gone through the procedure hundreds of times, and so it almost felt just like an exercise. We got the image, and that was fine. And then the terror started, because there was a month until we had this workshop to bring everyone together, and the terrifying aspect is, what if we could make an image, but no one else could? Right? What if we release an image, and it's like, well, here's our image, but we made these assumptions, or but they couldn't quite get the same thing, and we just had no idea what would happen there. So, I mean, for me, the absolute highlight was at the workshop, not seeing the images, but just seeing these metrics of comparison, this matrix on the screen flash up, show high correlation, and just instantly know everyone had gotten the same result, and that, we just had this rock solid result that we could, bet everything on. So,
and did you try Saturday Star with the same or was it completely out of the picture already in the comparison stage?
Well, at the next celebration, there's going to be great stories about it.
When is that?
So I'm Lindy Blackburn. I'm now staff at SAO. So this has been the best way I could have spent my last 4 or 5 years with the group here. I came from the LIGO experiment during grad school, and when I joined LIGO, I guess it was about as big as the EHT is now. So one thing I really loved about this part of the project was just seeing this tremendous growth phase from having maybe tens of people to the 200 or so we have now.
How many are actually doing the work?
There's a camera on.
But these guys do a lot of work. So many late nights with the group here, working out things especially over the last year. As things became really interesting and really tight as far as timelines. Anyway, so I think I had 2 major jobs here at the EHT. One is bringing up helping to bring up the LMT for first light with 1 millimeter VLBI. And I went out with Shep in 2015. We did that for the first time. It was I've been, I guess, technically an astronomer for a long time, but this was the first time I went to a big telescope on a mountain. LMT is really a frontier site, and it was really kind of like being thrown into the fire. But we got that working, and that's been a great experience in the last few years. And the second has been sort of managing and designing the data pipeline for the EHT. So for me, that's really interesting. It requires an understanding of the entire sort of end-to-end process of measurements and understanding the data. So I don't know, maybe because I've been on these 2 experiments and they both have this perception of being a really unbelievable project, right? But also a very difficult project. I like the opportunity of being able to tackle those problems, things that people might think are not possible, but.
Are you obsessed with black holes? It looks like that's the common thread.
But yeah, experimental relativity, black holes are fun.
What are you going to do for the rest of your life? After LIGO and EHT?
Well, there's this, there are lots of things. Anyway, let's move on. Okay.
So I started this project when I was a graduate student. I was actually working on very different things, nothing associated with black holes at all. And I went to this conference in Waterloo, the EHT conference, and at that meeting I met a bunch of people here. I met Michael and Lindy and Andrew, and actually the first thing we did is we went to see Interstellar in IMAX theater. I remember just leaving the theater and thinking, oh, they're going to tell me how this is all so wrong and all the physics is wrong, and I remember Michael coming out and being like, that was awesome! and I don't know, that I think what has made me stick with the project has been amazing and everything, but what has really made me stick with it is the amazing people that I get to work with, and the getting to learn from people much smarter than me around here at the BHI and around the world too. And then I think I agree with Michael that probably my happiest moment in the EHT so far is when, for me, it wasn't the correlation matrix, but it was actually seeing the images come on the screen. I have never been so happy that my method wasn't necessary to make the methods that I've developed weren't necessary to make an image, because I think that having the other methods, the traditional methods, also get the images and all different people, that was what made it really possible. Made us boost our confidence and made us really believe in what we were doing. And I think without that, that was the most amazing.
One question that was not addressed, at least in the public appearances, how did you know where the shadow should be? Because we know where the jet is, but it could be, the jet may be offset by some amount from where the black hole is. Or did you use the counter jet, or how did you know where?
There's just no information about that. What you see is what you get.
But you have a limited field of view, right? So you can't just. So did you shift it and look around, or?
Yeah.
How did you know where the shadow is?
Without absolute base information, you don't have any information. It's not like the shadow is relative to our image set point. So that's degree of freedom. And we don't see the jet in our images. So it's not like we place it by hand or anything like that.
So your field of view was big enough?
Yeah.
So that you could see.
So
we would have seen the jet.
Okay.
And we will in the future.
That would be very interesting to see if it's perpendicular.
It won't be offset though, because it's pointed at us. If it was edge on, you'd see an offset, but it's most likely that even if it's spinning, it's pointing straight at us, so there's not a displacement.
You mean that the spin of the black hole is pointing?
Most likely, because the jet is.
It's not a jet. It's not a blazer.
Well, it's
20 degrees.
20 degrees. I see. Okay. Thank you, Katie.
I'm Andrew. I work a lot on imaging and on numerical simulations. So this for me has been just the last 5 years of my grad school. I sort of came in first year. Met with Chef once and told me all about this project. I never heard about it. I had heard what VLBI was, but did not know about it at all. And I thought this would be a great thing to work on. I did not necessarily believe Chef when he said it was going to pay off in this way in 5 years. I remember him saying oh yeah, right when you're finishing, this is gonna pay off dramatically. We have these observations scheduled, and okay. But yeah, so for me it's just been those 5 years of grad school, just learning from this amazing group of people, particularly Katie, Ramesh, and Michael, and everyone else here. Just this whole group and all these diverse talents and expertises, and getting to know so much about all these different aspects of astronomy, and it's been an incredible experience.
And I should mention that Andrew was awarded, or will receive, the Eric Ito Prize of the ITC, the Institute for Theory and Computation, that is given for the best. Here is Eric Ito, that they gave us the mic. That is given the best PhD thesis in theoretical astrophysics, and he will be sharing it with the cosmologists. That we very much recognized the exceptional work that you've done. He seems very. One of his qualities, Andrew's qualities, is that he's very modest.
He's the most like that.
He's also outspoken when it matters.
Yes. That's why he's getting the award. I mean, we don't get the award for modesty.
Yes, I would say that like one of the other experiences of the EHT is me like learning that I do know what I'm talking about sometimes. So, so yeah, especially last year.
Anyway, yeah, I'm Daniel Palumbo. I'm a first-year grad student in astronomy here. I've been working with the EHT since my senior year in physics at MIT. So I've come down the road. In fact, I interviewed during the April 2017 observation. So I was like, why are they all so sleepy? Like, I seem really excited though. There's a lot of good energy here. But yeah, before then, I basically just built detectors for like particle physics experiments. So all I knew about was like computing scattering cross sections of plastics, and then suddenly there's this opportunity for really my first work in astronomy period to join the Event Horizon Telescope. And it has been an incredible opportunity and experience, and a lot of that is because of the incredible mentorship in the project. It is precisely zero hyperbole to say that I've learned something from everyone in the project, and everyone standing around here has taught me something that I will take with me forever. And I've been incredibly lucky to work with them, and I sort of fell into actually making some contributions, which is great, but it's just a pleasure to be a part of the family here.
And in the right place at the right time.
Exactly. Yeah, I got very lucky.
When I started, when we first got the BHI starting, we started talking about it in 2015 or so, early 2016, and we didn't know what it was going to become. We had hopes that these different areas would speak to each other in simulation and theory and observation, philosophy, and I mean, it's happened. It's really amazing in these 3 years, and in all sorts of different and unexpected ways. And one of them was that I hadn't planned on getting involved with the EHT directly. I mean, I thought I'd be filming and doing some other things, and but it was too interesting. I couldn't. I mean, there were times when I'd be filming and I just put the camera down and get into these discussions about what we were doing in the physics.
Like a
it was
psychologist
really
that gets involved. Gets involved with the patient.
But I once read something by young Feynman at the beginning of World War II, and he said they were thinking of the atomic bomb, and he said he was within this discussion in an old rundown building in Berkeley, and with Beta and Oppenheimer and all these people. And he said, I've never been in a discussion before where people don't repeat themselves. They just said, and then everybody understood, and they went to the next thing. I had that experience here in our discussions, and I loved it. It's magic. It's like suddenly people are speaking the same language, and before you were speaking in laboriously translating. And I enjoyed talking with the senior people, Mesh, and Shep and I shared that office and still do. And there were some wonderful scientific discussions, and then sometimes the telecom kind of head knocking against walls telecons, and I enjoyed that, and especially like working with this group of early career scientists who have become my friends and collaborators. I got such a kick out of learning from them, talking to them, figuring things out. I feel like we left nothing on the table in this project. Like everything we knew how to do, we used, whether it was statistics or imaging or new kinds of tests, or thinking about the philosophy of what it would take to actually demonstrate something. It's so fun, and it's just been such a kick. That's why I wanted to hold this. I want you all to come to my party tonight. 22-minute
It was never a physical kick. It was just what you meant.
Yes, it's really been great, and I'm so grateful to count all of you as colleagues and friends. It's really been a kick.
Thank you, Peter.
I'm Sarah. I'm from the other side. I'm a graduate student with Heidelberg in the Netherlands, and I joined the project kind of on a tangent back in 2014, already some time ago, just working on calibration of one telescope. And so I was just working on this one telescope, and then I got to go there in 2017 during the observation. I think that's really the moment where I realized we were part of something so big. It was just the coolest project in the world. Because I was at this telescope and we're all talking together on like a messaging thing, and we'd hear like, oh, LMT in Mexico is online, South Pole is online, and we're all talking to each other. Then you really kind of get the sense of, wow, what we're trying to do is really almost impossible, but we're doing it. And I think we've had a lot of these moments as part of this project, where we get down in the dirt and play with each other, and that's part of the work. But you get this moment at some point where you step back and then you realize what we've accomplished and what we're doing right now, and no one else has done it or is going to do it anytime soon because we're the only ones really doing it. And I think that was probably the best experience we could have in this project.
And it's a beautiful idea of having the entire planet collaborate, so to speak,
Yes.
rather than because usually we work in a specific country and specific working group, just establishing a planetary collaboration.
Yeah, it takes a global team for global tools.
Is there any other example of a planetary collaboration? Maybe it's the first.
All VLBI.
Okay.
Yeah.
Well,
All
that's
global
what I mean.
VLBI.
Global.
Yeah.
My name is Jordi Davelaar. I'm also from the other side, also working with Heino Valk as a graduate student. So the most intriguing memory that I have of EHT was this, when I saw Shep's message, April, when we got a go, and it was not a drill. Like, that is like engraved in my memory when I was like, I'm a theorist, so there's this saying that you shouldn't let a theorist next to a telescope because it starts to rain. So I was still at home in Nijmegen, but I felt so connected with like everyone around the world, and there was really this fight going on and people messaging, everyone was excited, and there was so much like positive energy going around. So that was really quite something that I still like carry with me, with like the memory to the first actual science room.
April 2017.
Yes, exactly. When the first go went for the actual first science room, so it was like I think a remarkable moment. But also when I actually saw the first image and I compared it with like the work that I've been doing for the 3 years and how remarkably similar it looked to like simulations that we were used to. That was also quite something to see like the whole project getting together, because we were always talking about you have the theorists and the observers, but at that point everything came together, and that was quite something, and I'm really grateful to be part of this amazing collaboration.
Thank you. Are you related?
I am related, yes.
Third cousin, once removed.
Right, yeah. I'm Dom Pesci. I'm a postdoc here at the EHT locally. And actually this time last year I was still in grad school, finishing up work and background I did I was in radio astronomy and studying black holes and things, but I had already realized, or I knew by then that I was going to be joining the EHT. I was pretty excited about that. But I didn't actually show up until the week of the imaging workshop that people have been referring to a couple times, where everybody first saw that everybody agreed with black hole. And that was pretty chaotic. And I was sort of like, oh, I guess that's it, right? Like, what am I doing here? I'm gonna be out of a job pretty soon. And then of course, that's when the work began. So that was pretty crazy. I think started out fitting. I have background in statistical modeling and feature extraction or parameter estimation, really. And started out fitting a couple of Gaussians, just trying to get things going. And ramped up pretty quickly from there. But really awesome group here. It's just very different from what I was used to. I worked at NRAO, and I was used to all the expertise being in the senior people, right? Like the sort of expertise that the average young person has around here is the level that I was used to getting from like senior radio astronomers at the National Radio Astronomy Observatory.
That reflects badly on the senior people here.
No, I no, the senior people here. No, sorry, I don't mean to. Jim Moran's here, right? Like this doesn't get better than that. But what I mean is that the level of knowledge and expertise in the young folks in the collaboration here is sort of a caliber that I was only used to seeing from people who had been in the field for decades, and it's just a huge learning experience and a real privilege to be able to join when I did. I'm very happy to be here and share this moment with everybody.
Thank you. Is there anyone else we missed?
David.
Carrie and Mislav are also outside.
Who else?
Carrie and Mislav are outside.
Yeah, Mislav's there too. Where's Mislav? And Carrie.
Okay, go ahead.
So my name is David James. I'm a project manager here for Shep's group. I'm essentially the buffer between Shep and everybody else. I protect them from Shep and Shep from them. So this is sorry. So yeah, I agree. It is. I think the thing I'm reminded on a daily basis is that it's a privilege. We're given this privilege by society, mostly, who fund us, but just the privilege to be able to work with you guys, very talented scientists. And I started off in X-ray and then went to optical infrared, and I fell into radio sort of accidentally when Shep gave me a call. I thought, I don't know anything about radio, what's he doing? But then I meet these guys, and you're right, every conversation you have, you learn something, and you don't repeat yourself, you're right, Peter. So it's a pivotal moment for my career, and so I feel just completely privileged to work with you all. So thank you.
Thank you. Anyone else outside?
Where's Mislav?
Yeah, where's Mislav?
Maybe he's not here. At any event, let's give a hand to all the EHT members. Cake that we have behind us.
Chef, you want to come cut?
Yeah, why don't Chef?
I can't eat raw cut.
Organize such a wonderful team.
The black hole cakes?
You should eat the shadow at least.
I'll say it. Should we just
in the meantime, does everyone have champagne or not everyone? Barbara, can we serve champagne to everyone?
I have.
No, there are
already.
some people that arrived late.
Oh, sure. Yeah.
Like edible sugar paper.
Very nice.
Your eye.
I know Andy.
Yeah, really.
Come on, thank you so much.
You said it follows us.
Was anybody else? You got it?
Here's four.
Okay, so what we would like to do is raise a toast for the EHT. Can I get I can get one for myself. Yeah, thank you. That's it. Thank you. Okay, so let's raise a toast to the success, the past success of the EHT and the future success of the EHT.
Wait, I gotta have more alcohol. Yeah, I'm not sure who this is, but I'll drink it.
Cheers. For many years to come.
I also want to acknowledge Avi's leadership of the Black Hole Initiative. It has provided a real home for the EHT. I think he pointed out that the walls in the film are these walls you see around us. So also thank you, Avi, for helping lead us.
Avi.
Thank you. And we will cut the cake and after that start with the program. Now, this evening at 7 p.m. there will be a party in Peter's home. I need to leave to Washington, D.C. shortly because I'm chairing a committee that oversees the Astro 2020 decadal survey. It's called the Board on Physics and Astronomy of the National Academy. So I won't be able to attend Peter's party, but I will join via Skype just for a few minutes. And we're grateful to Peter for organizing this wonderful party that all of you will come and some more people from outside as well. Thank you, Peter. So we'll start shortly as soon as Barbara finishes distributing the...
Yeah, do you guys want to help pass these out?
Why don't you give our speakers first, because they need to finish.
Yeah, that's I'm giving them. Oh, where's the speakers?
I'm good, thank you. 3 cakes, 3 champagnes today. I got 2 pieces. I wish for having
That's too big.
Yeah, I'm just gonna have one.
Do you guys want cake? There's one here.
It's fine.
You represent the dark side.
The other side.
Yes.
I didn't say the dark side.
No, thank you.
No? I'm good,
Thank you. You should say the dark side. That would be fun.
What makes you think this isn't the dark side? I've been brainwashed from the other side.
That's true.
This is the dark side. What?
No, thank you, but thank you anyway.
So I said the other side.
So you have a foot in both camps, right? You're sort of like Ray from the Jedi film. You're half light, half dark.
Vanishing an epsilon,
Dangerous.
one, and you're good with
I'm like a spokesperson for both sides. I don't like it. I don't like it. I don't want to be this person.
See you guys. Are you? If I resign tomorrow, I can screw a lot of you up. Delete all your database entries, everything.
Oh no, I wouldn't be able to interact with people.
Nick would be so happy, no teamwork.
I like it all. This is comparison group.
Now that's a good point.
This effect is just gross.
Have you looked at a petition?
Yeah, of course.
Because then people bitch and moan when they don't have access to TV.
Yeah.
Oh my gosh, that was the scariest. We didn't pay our team much.
Oh, I was there was a
Really?
Yeah. They said you haven't paid your bill, and we're going to delete everything next Tuesday. What?
At least I sent an email.
Yeah, at least they warned you.
Yeah, Max.
Well, I think they have a backlog. They have to pay to get it back.
Clever.
That's so fun.
That's why they're in business and we're not.
You can't really tell from the resolution they have now, but in 6 months they'll have more data, and it may be possible to say how fast it's getting.
That's a great title, by the way. I thought they make Janssen.
Yeah, same.
There's the other
These two Sagittarius triangles that are really
Michael Johnson, Michel Janssen. Like Michael Johnson is the English translation. That's Michel Janssen. We have the German version of Michael Johnson.
what you could imagine. They will come with it eventually.
So we're curious what would happen if the two meet. Do they annihilate?
Historically, that's never been a good thing. Last 100 years.
They lost and they survived. So apparently they're not the anti-Is
there, what would be your opinion? Your view is George? And Davila?
There's no translation for that, I guess.
There's probably a guy living in Bristol called Davila or Davila.
And so I think
we should see
MH7 people will be at least 70%.
Are you staying for this talk?
But I think it's over 90%.
When do you go? You're back tomorrow?
Tomorrow, end of the afternoon.
Oh, right.
We still have the full day tomorrow.
What time is your train?
My train is at 5:30.
From South, what station?
What's it called? Back Bay.
So, yes. Oh, you have to go to Back Bay? Yeah. So you can get the right line?
Yeah, or just grab an Uber and make sure that
Well, we're going to the park this afternoon to watch football.
Good version.
Manchester United, Manchester City.
The black hole go around. There you go around.
Yeah, I might want to. I have a couple of people still on the list that I want to talk with. Yeah, well, but it will take also an hour or something. Or 10
that's true.
Oh, that's the hook. So the special thing about the very
He said Michel.
Yeah, do you want to walk over?
It is written.
Ramesh said Michael.
That's an interesting way to read it.
Ramesh said Michael.
So an Indian speaking English about German.
It's a Dutch guy.
Oh, really?
Yeah, he was from the University of Amsterdam.
Oh, really? He's Dutch?
I spoke Dutch with him. We arrived around the same time already yesterday. I do. Yeah, really. Yeah, I know, right? Yeah, I know.
This is weird.
She can't use it.
It's the corner of GR that's in the parts.
It's like the bear and the chicken.
That's also what I want to know. Sarah, who's the bear, who's the chicken?
Alright, well I'll be around tomorrow.
Are you going to the party? But until what time do you teach? The party's until 11.
Yeah, so I teach up in the north, about 50 kilometers north of here.
50?
And I live 50 kilometers north of here.
Oh man.
So it's just
That doesn't make sense.
Well, what about tomorrow lunchtime? Do you want to go out for lunch probably? Yeah. It's actually a really cool place. Road here, kilometer away, and they do great sandwiches, but it's really
Sure. I don't have any lunch breaks for tomorrow, so that's great. We can hang out with some people and just have amazing lunch. There is
maybe.
But in 6 months, you're going to get so not just the intensity of the they just haven't extracted it. First of all, they have to have
people here, I can stop saying
and you don't have any power except team.
I don't know. They just apply to
That's a good question. Okay, yeah.
That's why you
underestimated your power. That's also what you said.
Publicity, you know, the whole announcement. Spike of
Alright, well, I've got a meeting at 2, so when should I meet you down here about midday?
So it's expensive.
Yeah, let's stay in contact. I have your number, you have my number. I'm fine. Yeah, but what is it? 12:30 or something for food?
Yeah. So if we don't get in contact, which we will, maybe outside here at 12:30. I'll go
It's what I thought.
Sounds great to me. See you tomorrow.
The price is set by how much they need to build the telescope, which is a lot of money, but they're not turning a profit. And then you have to convince other people that your science is that's really hard. I'm not sure. It's not trivial. Because like, you know, in Jefferson, there was this experiment running for decades, the electron clock. It was trying to sensitively measure the electron dipole moment, so it's to align with the background. And every decade, that experiment will spit out the next decimal in that constant of nature. So it's a super boring experiment. You just have to see the output is every 10 years. But so that would be fun. I think nobody cares enough. But I guess everybody's betting that they'll match the calculations from QEDA. It's a higher order. They have so far. It's the most exclusive agreement between the theory and experiment as well as science. It's predicted effect, which has been measured and tested. There's nothing like that.
As the summer goes in, they'll be taking I don't know.
So it's an experiment which is the best science field. It's so boring. So I think it's the opposite, where the word is an invention everybody gets instead of a science is first. It's like science
slightly different things.
For the science too. What are we going to learn? And they're competing against other people that say, well, I want to do this telescope to be pointed at, you know, this galaxy to measure this is quantitative effect. It's kind of ruthless.
What? I had a thesis defense that it's my third day. I picture my second day.
Okay, so perhaps we can get started. I'm delighted to welcome Professor Michel Janssen to the Black Hole Initiative Colloquium Series. Professor Janssen is a historian of modern physics, and he works in the program of History of Science, Technology, and Medicine, as well as a School of Physics and Astronomy at the University of Minnesota. He's worked extensively in the history of general relativity, some of which we got to hear about yesterday, the lovely workshop that he gave as part of the EHT philosophy working group. He also works extensively in the history of quantum theory. As I understand, he has a book coming out about this very soon. Today, he's going to tell us about how Einstein found his field equations.
All right. Thank you very much for us. Thank you, Peter, for the invitation. It's a tremendous honor to speak here. And this is you understand this is a very tough act to follow. Okay? So, but I have something I think going for myself. So I'm going to talk about how Einstein found field equations. So basically, it's about events leading up to November of 1915, where in the beginning of November, Einstein replaced equations that I can use this, replaced the equations that he had published 2 years earlier, known in the historical literature as the Entworth or outline equations, which are equations of severely limited covariance, by equations of much broader but not yet general covariance, namely they're covariant under general unimodular transformations. So then, he came back to his colleagues, and I'll explain to the end, why he is publishing different field equations in rapid succession here. He came back and realized that he could make these November 4th field equations generally covariant by making the rather dubious assumption that the trace of the energy momentum tensor is going to vanish. Then in November 1918, on November 18, he had the event that I was reminded of listening to the proceedings earlier, where Einstein reported this gave him heart palpitations. He was beside himself. He couldn't work for days when he plugged in the numbers of a new calculation of the perihelion motion of Mercury, and out popped the missing 43 seconds of arc that could not be accounted for on the Newtonian theory. That was not the end. He came back one more time to change the field equations one more time, now making the field equations of November 4th generally covariant, not by making a dubious assumption about the trace of the value of the trace of the energy momentum tensor, but just adding a term with the trace, and then he had it. Okay. Fortunately, that did not affect the calculation of Mercury. Now, in the interest of time, the progression from here to here is kind of interesting but hairy. I'm just going to focus on this story, how we got to November 4th. The rest is kind of yes.
Would it have affected the prediction for bending of light?
No, it would not. I should also say, I've been given 25 minutes to go through.
Okay, I'll shut up.
Right, so I'm going to go at a very fast clip. So I'm asking you to please hold questions. I mean, I could literally talk for an hour on just about any question you have. Okay, so please hold your question till the end. Okay, so I'm going to look at what I think is the real breakthrough here, the first November paper. And Einstein in the paper, he reports, I completely lost confidence in the field equations, the old ones, the Entworth equations. I was led back to the demand of a more general covariance of the field equation, which I had abandoned with a heavy heart 3 years ago when I was collaborating with my friend Grossman. In fact, back then we already came very close to the solution of the problem given below. And then he goes on to say, hardly anybody who has truly understood the theory will be able to avoid coming under its spell. It's a real triumph of the method of general differential calculus. This before the theory is generally covariant, developed by Gauss, Riemann, Christoffel, Ricci, and Levi-Civita. And then he says, after what's been said so far, it's natural to posit field equations of this form, where R mu nu is not the Ricci tensor, but half the Ricci tensor. Okay, I'll show you that in a little bit. Now, so this is now feeds into the story that Einstein just got this by taking the mathematically most elegant candidate. What I'm going to tell you is that is in fact a very distorted version of what's actually happening. Now, he was certainly right that he got close. So we have the notebook, it's the famous Zurich notebook, and on page 22R, you see the name Grossman appearing, and there what you see is the Ricci tensor. And so Einstein now says, okay, let's look at the special case that the determinant of the metric is a scalar. In that case, the derivative, the log of the square root of g is going to be a vector, and that means or a tensor of first rank. That means if you take the covariant derivative of that, this will be like a second rank tensor under unimodular transformations. Since the whole thing is a generally covariant tensor, it means that the second part also has to be a tensor under unimodular transformation. So this is going to be the vermutliche Gravitationstensor, the probable gravitation tensor. That's going to be the left-hand side of the field equations. And so this is what is called R in the 1915 paper. So this thing returns in the November 15 paper, And the question is like, so this is only a few tweaks away from the final field equations. And the question is like, why did he reject them before? And the answer is, as Einstein himself tells us, that he thought they violated energy momentum conservation. He did not see how you could get the Newtonian limit out of these equations. Now, so what was the problem with the Newtonian limit? If you look at Pisces, which is still the best sort of scientific biography of Einstein, even though it's like quite outdated, from 1982, he says like Einstein and Grossman did not know about coordinate conditions. Okay? But as John Norton, my advisor, shows, in the Zurich notebook, Einstein already had is applying coordinate conditions to extract, to show that these equations reduce to the Laplacian under the right conditions. And here's a proof of it, right? So he is looking at this particular one, half the Ricci tensor, and he is like imposing this condition, which in modern terms is just the vanishing of the ordinary divergence of the contravariant metric, and shows that all you've left is this. This is like clearly the so this is going to reduce to the Laplacian acting on the field in the static case, plus terms that are quadratic in first order derivatives, which are negligible at in first approximation. So this is a perfectly fine way to get the Newtonian limit out, and this is in the notebook. So what is the problem? Now, John Norton speculated that the real problem is that the rotation metric, and by that I mean the metric of a Minkowski space on the rotating coordinates, does not satisfy this coordinate condition. And it was very important for Einstein that that metric is allowed, because that was what his whole idea about the relativity of rotation is sort of based on. Now, a lot of that is like completely illusionary that this would work, but this was an important part of Einstein's heuristics. So now the problem is that if you take that probable gravitation tensor, half the Ricci tensor, and you impose that coordinate restriction, that the rotation metric is just no longer a solution of that. Okay? And that's, as John Norton argues, is why he abandoned it. Now the question is like, why is that a problem? These coordinate conditions are of course gauge conditions, so different problems, you have different conditions. Why would you insist that the same condition that gets you the Newtonian limit would also get you like rotation? There's no reason to do that. So, and moreover, like in November of 1915, when he resurrects this, he doesn't see a problem with this at all, because he does impose this condition and then goes on to say that rotation now works on fine. So what was the problem? So this is like the work that Jürgen Wren and a group like consisting of like John Norton, John Stachel, Tilman Sauer, and myself have published in 2007, and that is that Pice was not completely wrong. Einstein had a very funny understanding of coordinate conditions. So instead of like taking different conditions for different problems, he took the sort of one-size-fits-all approach and felt that once you committed to a particular coordinate condition, you were stuck with it throughout like the development of the theory. So we call these things coordinate restrictions. So that means that for Einstein, field equations before November of 1915 have the following form. Ideally, you start with some general covariant equations, then you impose your coordinate restriction, you use that to truncate these equations, and what you've left, those are the field equations. Okay? Not field equation in a particular gauge, those are the fundamental equation of the theory. And so these coordinate restrictions did sort of triple duty for Einstein, so they need to ensure that you get the Newtonian limit out, that they felt that you also needed to restrict the covariance to get like energy momentum conservation to work out, and you need to preserve enough covariance after doing all that so that you can implement these, in hindsight, misguided ideas about the relativity and the equivalence principle. All right. Now, many of you will have noted that if this is your condition, that basically you're knocked down all the way to just transformation in covariance of the linear transformations. You're not like generalizing things at all. Now, Einstein has a trick for this. He is looking at what he calls non-autonomous transformations, where the new coordinates are not just function of the old coordinates, but function of the old coordinates and the metric tensor in those old coordinates. Now that sounds like very, very fancy, but it's in fact the sort of thing that a novice in differential geometry might think of. Write down the transformation law for this thing, you get what you want and a lot of crap, and so you set the crap to 0, right, and that is your coordinate restriction, that's going to depend on G mu. That's all that's going on here. This is just fancy terminology for this rather naive approach. So, despite all that, Einstein could not find any coordinate restriction to apply to the Ricci tensor and be left with something that he liked, so he switched to a physical strategy where you just cook up a field equations for the metric field, not worrying about connecting them to anything in differential geometry, but equations that just are modeled on the Maxwell-Lorentz equations in four-dimensional formalism. And you make sure that you set them up in such a way that you're guaranteed to get the Newtonian limit out, and that you're guaranteed to get the energy momentum conservation right. So Einstein modestly calls this is Edworth, the outline of a generalized theory of gravity and relativity. Generalized because he has no idea how general this really is. The covariance properties of these equations are completely untractable. So now what he does the following years is to elaborate this theory, and he comes up with the idea, suggested to him by a mathematician, Paul Bernays, to cast the whole thing in variational form. So, and he's going to do this like, just mimicking what you do with the electromagnetic field. So first off, the field equations. Here it is in electromagnetism. Here it is in gravity. And the basic idea is just that you do something of the four divergence of the field, set that equal to the source. Okay? And Einstein realizes that the source in this case is going to have to include the gravitational field itself, because of E equals mc squared, that's going to carry its own energy and will produce like a field. Hence, like these equations are horribly like nonlinear. All right. Now, the other thing that he takes from the analogy with the field is that, okay, the metric tensor is the potential. What is the field? Well, in electromagnetism, in electrostatics, of course, it's simply like the gradient of the potential. In general, it's going to be a little more difficult, like it's going to involve the vector potential. In the four-dimensional formalism, you get two terms, both like as derivatives of the four-vector potential. So, but the gestalt is obvious enough, right? You want something minus the gradient of some potential. So Einstein, quite sensibly in 1913, chooses, forget about this bit, just a straight gradient of the metric. Now, he could have done something else, and in 1915, he actually chooses, instead of this, just three terms like that, just what you have like in A mu nu and A mu mu, and then it becomes like the famous Christoffel symbols. Now finally, he's going to define like Lagrangians for these equations. So like the Lagrangian for the free Maxwell field is this. So the gestalt is that it's basically like a field squared. Well, we know how to do that, right? This gives you the vacuum field equation. So take the Lagrange, take the field squared over here, and bang, you get like these vacuum field equations. Very nice. Now, Einstein also notes that one and the same condition on this theory gives you two things. It ensures that the condition ensures that energy momentum conservation is being respected, and it gives you the extent of the covariance of the theory under these funny non-autonomous transformations, which by now he calls justified transformations between adapted coordinates. Right? So here is the idea. Here's the Lagrangian that gives you these field equations. So now, in order to guarantee energy momentum conservation, the ordinary divergence, the sum of the matter energy momentum tensor and the gravitational pseudo tensor has to vanish. That's equivalent to like the covariant derivative of the ordinary matter energy momentum tensor vanishing. And you can see how to do this. Well, if you impose that taking the derivative of the left-hand side here is going to guarantee that the right-hand side will do that too. That is the condition that Einstein writes down as B mu. In the general covariant formalism, that same strategy would get you the contracted Bianchi identities. Now, I can't show you in detail how this works, but this condition doubles as the restriction on the coordinates. And so basically the structure of the theory now is that you have the field equations, you know what they are. Einstein believes that they correspond to some generally covariant field equations, but he doesn't know what those are, but doesn't care. But he does know the coordinate restriction that extracts them from these. So by analyzing this, you can get a sense of like what the covariance properties of the theory really are. So, and what you have here is that this link between covariance and conservation sort of looks like the Noether theorem of von La Lettre, and of course Noether in 1918 discovers the Noether theorem in the context of like clarifying this in the final theory. Now Einstein also like contributes to the work of his competitor Nordström, and he does the same sort of thing. So the field equation is going to be some generally covariant equation plus a coordinate restriction. In this case, it's just setting he knows the generally covariant equation, it's just setting the Riemann scalar equal to the trace of the energy tensor. The coordinate restriction is now that you write the G mu nu as a conformal factor times the Minkowski metric, and then it works. And so I'm just showing you this to show you that Einstein thought of field equations in this particular format. Now he had an argument, and I'm not going to cover this argument in detail, that showing that you could not possibly have generally covariant field equations. This is the famous Hall argument. And the basic idea is you can trivially write, if you have a g of x, I'm suppressing the indices, as the g prime of x prime, but the mathematics doesn't care at all what the x prime is referring to. So you can read the x prime as essentially coordinates with respect to your original coordinate system. And when you do that, you see that a metric that is assigned to one point by one of these things is going to be assigned to another point by the other, which means that now it looks like the whole thing has become indeterministic. Now Einstein comes up with an argument against this in 1915, and basically this hinges on recognizing that these things do look different, but they in fact are not. The basic assumption you should not be making is that these bare manifold points in modern terms have what are called primitive distness, or hexiety. Hexiety, that's how you pronounce it. It's George W. Bush needing I'm a dinner jacket to remember how to pronounce Ahmadinejad. It's hexiety, right? They don't have hexiety. In fact, what becomes a space-time point, different bare manifold points become different space-time points depending on which whole diffeomorph in modern terms you use to dress up the bare manifold to become a space-time. Now, for Einstein, these arguments are basically just fig leaves. The first argument is a fig leaf to cover up the fact that you don't have generally covariant field equations. The second is a fig leaf to explain why he went back to generally covariant field equations after he's published 4 times this argument that you can't have it. Okay? So, I'm going to skip this in the interest of time. The upshot is by late 1913, Einstein is perfectly happy with this theory. It's not generally covariant, but he thinks he has a perfectly good argument for why it can't be. So now he leaves in March, he leaves Zurich for Berlin, and a new woman, his cousin Elsa Lowenthal Einstein. And in late 1914, he convinces himself that energy momentum conservation actually uniquely fixes the Lagrangian for the theory. And so he is now publishing a lengthy review article on this theory in the Proceedings of the Berlin Academy, and the modest title of Outline of a Generalized Theory is now replaced by the very immodest title, Formal Foundations of the General Theory of Relativity. This is still the old theory. In the fall of 1915, the whole thing starts to crumble. In late June, early July, he gives a talk on this theory in Göttingen. It's attended by Hilbert. Hilbert is very quick on the uptake. And the moment that Einstein starts finding problems, he realizes that he had limited amount of time to come up with something better, because otherwise Hilbert is going to beat him to the punch. So the first thing that he finds in September of 1915, he finds that this rotation metric that crucially had to solve the equations is actually not a solution at all. And this is kind of an embarrassing story where Einstein flip-flops for 2 years, and we have documents proving this, where it's a very simple calculation, but he manages to screw it up over and over again, and sometimes he concludes that it is, sometimes he concludes that